Hello everyone, welcome to the lecture series on IC applications. In this lecture we are going to discuss on various types of differential amplifiers, the basic characteristics of uh, operational amplifiers. As a part of this lecture session, we are going to see various types of differential amplifiers. Now let us see what are the various types of differential amplifier. As you might have come across in your early academic stage, we know that the diode. So what are the various types of diodes? So any electronic device can be categorized into two types. One is practical, and the second one is ideal. So before we categorize or classify the differential amplifiers into two types. So even in the differential amplifier, there are two types. So one is the ideal operational amplifier and the other is practical operational amplifier. So why we are suddenly bringing the term operational amplifier? So that we know, we have seen in the basic building block diagram. The basic block diagram of operational amplifier consists of three number of stages. So what are the three number of stages? First will be the input stage, second will be the intermediate stage, and the third one will be the output stage. These are the three stages that an operational amplifier do consist of. Now what are the components present in the input stage? It is nothing but cascading of differential amplifiers. A minimum of two number of differential amplifiers are cascaded as a part of the input stage. Now, so that we have seen in the previous lecture. That is, what are differential amplifiers? What are various types of differential amplifiers? So we have seen there are four basic types. Depending on the input and output configuration, the differential amplifier do consist of two transistors. So one is Q1 and Q2 we will say, whereas the output is collected between the collector of the two transistors. So that is the difference of the two transistors. Output is obtained here. We do provide two input signals. So one is nothing but V in 1, the another is V in 2. It is nothing but dual input differential amplifier. If both the inputs are available for the given differential amplifier, we will say that the differential amplifier consists of two inputs. There are two exciters or generators. They do activate the two transistors accordingly. And now, if both the transistors are providing the output, which is obtained across the collector of the two transistors, nothing but balanced output. So this we have seen. So what is it? The differential amplifier has four types. The differential amplifier has four types. So one is dual input. So let me say that dual input balanced output, DIV. And the second one is dual input unbalanced output. Third category, single input balanced output configuration. And fourth one will be single input unbalanced output configuration. So these are the four types of differential amplifier that are available for configuring. We can have these four possible configurations for any differential amplifier. And most frequently used differential amplifier is going to be dual input balanced output. As we said, both V in 1 and V in 2 do exist in the circuit, and the output is obtained across the collector of the two transistors. And what about the emitter? You know that both the transistors are in common emitter configuration. Both Q1 and Q2 are in common emitter configuration, which means both V in 1 and V in 2 are connected to base of the corresponding transistor. Base terminal is excited by means of a function generator, or nothing but a sinusoidal input is provided to the base of the two transistors as V in1 and V in2. What about the collector? As we said, the collector terminal of the two transistors is used to obtain the output. The output is obtained across the two collectors of the transistor. The third terminal, what about the emitter? So here we do consider the configuration, that is emitter coupled configuration for both the transistors, right? So these are the basic configurations that do exist in the differential amplifier. Now what about the bias? So since we are using the transistors as an amplifier, so the major important component in the circuit is nothing but bias. So what about the bias in differential amplifier? So if you remember, in the basic amplified circuit such as CE, common emitter amplifier, or common collector amplifier, or common base amplifier, biasing plays an important role. So that allows you to fix the Q point. Appropriate biasing is required, biasing voltage, and this biasing is will allow the Q point to fix in appropriate location. That means by considering both the resistors and everything, you are going to set up the Q point as per the requirement, right? So there we use only one biasing, that is plus VCC. It may be 5 volts, 10 volts, or 12 volts, 15 volts, according to the gain you need, according to the design of the given amplifier. We set the appropriate voltage for biasing. Similarly, in the differential amplifier also we do provide biasing. Here we have two types of biasing. One is plus VCC and another one is minus VEE. That is, one positive bias is provided across the collector terminals of both the transistors. So plus VCC is provided to the collector terminal of the transistors, and minus VEE is provided to the coupled emitter terminals of the transistors, right? So minus VEE is the negative bias which is provided to the coupled emitter terminals of the transistors. So this is what we have seen in the last class. So we have seen various types of configurations for differential amplifier. So what is the circuit nature, how we construct for dual input balanced output, how it looks, and what is the circuit nature for dual input unbalanced output. Unbalanced output means only one collector is used to get the output. That is that the output of the differential amplifier is obtained from either of any one of the collector terminal. What about the other collector terminal is usually connected to the ground. That means the output is obtained from the only one collector. In the case of single input, as we said, in the case of dual input, we have both V in1 and V in2 considered. And here in single input, there will be either V in1 or V in2. It is not required to apply both. It is not required to apply both V in1 and V in2 for the given differential amplified circuit. Right, that is what the single input. And balanced output is always obtained across the two collector terminals of the transistors. And similarly, single input unbalanced output we have seen. Again, there will be only one input, either V in1 or V in2. So what is by either V in1 or V in2? That is, we have two transistors, Q1 and Q2. We have two transistors, Q1 and Q2, out of which maybe either Q1 is connected to V in1 is connected to base of Q1, or V in2 is connected to base of Q2. So it is not mandatory or required to apply both inputs to the corresponding base terminals of the transistors. Right, it may be either Q1 will be excited by means of external generator, or it may be Q2 will be excited by means of your external function generator, right? That is the meaning for single input. And we know about balanced and unbalanced. In the case of balanced, both the collector terminals are strictly used to get the output. Across these two, we are going to get the output. So if you see, these are the two collector terminals of Q1 and Q2, the output is obtained between the two collector terminals. So which is usually considered as a difference between the two outputs. So why? Because Q1 will produce an output called VO1. The output across V1, the output across the transistor Q1, the collector of the transistor Q2 is nothing but VO1. And if we say the output across the collector of the second transistor Q2, that is VO2. Now what is that output now? The final output voltage VO is the difference between the two, right? And accordingly, that we will see how to derive the expression for differential gain AD. Differential gain AD. What is the expression for differential gain AD? It is given by VO by VO1 by, the differential gain AD is given by VO divided by V1 minus V2. Right? So this we will see in the next class. As of now, we will discuss the basic types of operational amplifiers in this lecture. So, as we know, the symbol for the operational amplifier. So, it is just like the symbol for operational amplifier is a triangle. I can say this is a sleeping triangle. Why? Because you know the symbol for triangle. This is the symbol for triangle. It looks like horizontal. That means it's just like this. If somebody have given a hard hit on one side of the triangle, so suddenly it fell down. Then what will happen? Now the triangle looks like this. So this is the triangle. This is the basic symbol for operational amplifier, and it consists of standard number of pin configurations. So the first and foremost IC is nothing but IC741. We will see the pin configuration for IC741 in the upcoming classes, and pin details, everything we will discuss. As of now, to categorize the types of differential amplifiers, so which are basically of two types. So try to understand the symbol for operational amplifier is a sleeping triangle, right? And it consists of two inputs. What are the two inputs? So first input is called non-inverting input. So first input is said to be a non-inverting input, and the another input is going to be inverting input, right? And opposite to this side, there will be one more pin that will give us the output. So here you are going to get the final output of this integrated circuit or operational amplifier. So as of now, try to understand the input and output representations of operational amplifier. So what are they? There are two number of inputs. What are they? One is non-inverting input. Another one is inverting input. What is meant by non-inverting input? The signal, that is the input signal applied to the non-inverting terminal, let us say Vin. Let us say the signal as Vin1. The input signal applied to the non-inverting terminal will have a polarity of plus. Understand? And similarly, the input applied to the inverting terminal, so let us say this as Vin2. The input applied to the inverting terminal will have a polarity of minus. That is a meaning for inverting and non-inverting, irrespective of the original signal nature. Suppose if we apply a signal with polarity of minus, so what happened when the signal approaches this inverting terminal? It will opposite the polarity. So the signal available at the inverting terminal will be minus of minus Vin1. So which is going to be plus Vn1. Right? Do understand the signal available, the signal that is applied across the inverting terminal will have a polarity of minus, and similarly the signal applied across the non-inverting terminal will have a polarity of plus. So these are the two standard inputs. So one is inverting input, another one is non-inverting input available in the basic operational amplifier. So which we call it as IC 741. Right. And as usual, there will be only one output, which is V0. Right. Now let us see this ideal operational amplifier and practical operational amplifier. What are the differences? What are the differences between ideal op amp and practical operational amplifier? So what is meant by ideal? What is meant by practical? So we said the diodes are again of two. What are they? We can say ideal and practical. So let us recollect the basic nature of the diodes. So what is meant by ideal diode and what is meant by practical diode? So the diodes are defined by means of its characteristics. So one can differentiate or distinguish this ideal and practical in terms of their characteristics. That is one way. Another way is in terms of the input impedance and output impedance. In terms of the input impedance and output impedance, one can categorize this device. Right? Let us drive directly into the operational amplifier. So what it says, in the case of ideal operational amplifier, if you look at the input impedance, this is an amplifier. What it consists of? Similar to your basic common emitter, common base, common collector amplifier, what an amplifier consists of? It consists of impedance and gain. Impedance and gain. And now we are going to categorize this operational amplifier in the context of, as of now, in the context of impedance. So this impedance is further categorized into, we are going to have input impedance, let us say Zi, and output impedance, that is Z0. Right. So this plays a major difference. This is a major difference between ideal and practical differential amplifier. So let us see what is the input impedance. So let me review once again. The basic operational amplifiers are categorized into two types. On what base? How we are going to categorize them? Based on the property of impedance, based on the nature of impedance. That is input impedance and output impedance. If we look at here, we are going to say that input impedance is infinite and output impedance is 0 ohms. So what is it? For a given ideal operational amplifier, input impedance Zi is sufficiently high, which is supposed to be infinite, and output impedance Z0 is as minimum as possible, which is supposed to be 0 ohms. Clear? So these two things are truly not possible. It is hard to maintain or achieve input impedance infinite ohms in practice. So these things are applicable on or for ideal operational amplifier only. So why we need to maintain infinite in the sense, we are going to say that the input impedance should be sufficiently high. This is a reasonable statement, acceptable statement. If somebody says suddenly impedance is infinite ohms, infinite means what? Do we have any significant value for the infinite? So this is applicable. The statement is applicable for the ideal case only. In practice, in practical case, we are going to define certain number of ohms. It may be mega ohms, as we said, sufficiently high. Mega ohms are, we can say that 100 mega ohms or 200 mega ohms, like that one can define impedance. Right? In the case of ideal, one can define this impedance as infinite. Right? And similarly, what about the output impedance? Output impedance is assumed is set to be as low as possible. Again, one cannot maintain this 0 ohms across the output terminals. It is hardly possible. There will be at least few amounts of ohms. That means there will be 100 ohms, 200 ohms, at least there will be 50 ohms in the case of a practical scenario. This 0 ohms is applicable only for when we are discussing about the ideal case, right? And these truly do not exist. Ideal devices do not exist. On paper, theoretically, one can give statements like this, right? And even in the case of a diode, the VI characteristics, if you remember, the VI characteristics seems to be like this. It is gradually increasing after the cut-in voltage, 0.3 or 0.7, depending on the material, silicon or germanium. This is for practical scenario. And in the case of ideal case, we will say that the current starts increasing instantaneously the moment you start increasing the RPSU from 0 to fractional increment in the voltage is sufficient to raise the current, to see the current in the diode. That is what in the case of the ideal case, right? So, and one more question. So why we need to have the input impedance sufficiently high? Why it should be always high? What is the reason? So means, as we know that this is your input section. This is your input section where we are going to provide some external input. We are going to connect some external input to the device. It may be either your op-amp or transistor or whatever you say. So here we are giving some external signal that is going to play with the active device, that is a transistor. So this impedance should be sufficiently high to damage this active device. It may be op-amp or transistor because of this sudden incoming signal from the external ports, right? So that it is always required to maintain the input impedance sufficiently high. And in the case of ideal scenario, it is supposed to be infinite. And another question: why we need to maintain output impedance as 0? It is not 0. It is as low as possible, because from the output, the output of this circuit is connected to some external circuit. It may be a loudspeaker or any other circuit. The output of this circuit, so whatever we are going to obtain here, it is supposed to drive some external circuit. This output signal is supposed to drive some external circuit. So what matters here? That external circuit should match with this op-amp circuit. So here plays an important parameter called impedance matching. In order to meet that impedance matching criteria, the output impedance is supposed to be sufficiently as low as possible. And in the case of ideal, we said that this value is 0 ohms. Right. So these are the two important characteristics of ideal operational amplifier. What are they? The input impedance should be infinite and output impedance is supposed to be 0. So this is ideal case. And here we are going to list. Further, we can give the characteristics of this ideal operational amplifier. What are they? The input impedance, as we said, it is infinite and output impedance is 0 ohms. And again, the open loop gain is sufficiently high. But in the case of ideal case, we said that it is infinite. And similarly, bandwidth is going to be infinite. What is the meaning of this infinite bandwidth? Will amplify the signals of any frequency without any attenuation. Truly, in practical scenario, this situation is very hard to realize. So these are on paper theoretical statements, right? So at least we can understand which parameters should be sufficiently high, which parameters should be sufficiently low, right? And another parameter, common mode rejection ratio. So as we said, the different what is the major block in operational amplifier? It consists of differential amplifier in the input stage. It allows only differential gain. However, it's supposed to reject any common mode signal. That is, all the kinds of common mode signals should be rejected, which is nothing but common mode rejection ratio. So it is supposed to be high in practical case, and here it is said to be infinite. Common mode rejection ratio should be sufficiently high, and here it is infinite. That means, so this ideal operational amplifier strictly denies any kind of common mode signal, right? And coming to the slew rate, so that we will see the rate of change. It talks about the rate of change. It is again sufficiently high, and it is supposed to be infinite in the case of ideal op amp. So which means the op amp will produce a change in the output instantaneously in response to an input step voltage. So these are the basic characteristics of ideal operational amplifier. Now coming to the practical operational amplifier, here you can notice you can find the equivalent circuit for practical operational amplifier. So in the case of ideal, we said it is infinite. Input impedance is infinite. Infinite means what? So we said it is like a open circuit, right? And here we have a sufficient amount of impedance with some ohms. It may be 100 ohms or 1 kilo ohms or 1 mega ohms preferably. So because the requirement is Zi should be as high as possible. The input impedance should be as high as possible. So here we are going to maintain a finite amount of resistance across the input terminals. And similarly, in the case of output impedance, what is your output impedance? We said it is a short circuit. So which means there is no impedance, 0 ohms. In the output, in the case of your ideal scenario, ideal operational amplifier, the output terminals seems to be short circuited, which leads to a 0 ohm resistance. And here in the case of practical situation, there is a sufficient or definite amount of resistance will be available in the output ports. So with some resistance, preferably small value. The output impedance should be as low as possible. So this low is to achieve impedance matching with external circuit, and this high is required whenever we are applying some external signal to the operational amplifier in order to protect our complete circuit. So input impedance should be as high as possible and output impedance should be as low as possible in order to meet the impedance matching criteria, right? So these are the this is what we can say practical operational amplifier. And let us see the characteristics of practical operational amplifier. What are they? It exhibits some amount of resistance. So you never find the two values such as infinite you cannot find, and similarly 0. Both infinite and 0 do not appear in the case of the practical. Now coming to the characteristics, the input impedance Zi is of the order of few mega ohms. As we said, it is sufficiently high. And similarly, the output impedance Z0 is of the order of a few ohms. Maybe approximately one can define it as a 1 kilo ohms output impedance, as we said, sufficiently low. And similarly, open loop gain, in the case of ideal it is infinite, and here we are going to say it should be as high as possible in order to meet the design requirements. The open loop gain should be as high as possible. And similarly, so what is another parameter? Output impedance is as low as possible, and gain should be high as possible. And CMRR, whatever the CMRR and bandwidth slew rate. So what is your bandwidth in the case of ideal situation? So there it is defined as infinite. So what is my infinite bandwidth? So the amplifier will amplifies the signals over the entire frequency band without any attenuation. Here it is not like that. There will be a bandwidth of, we can define that as something like 300 kilohertz. So there will be some finite value, 500 kilohertz, some kilohertz of bandwidth is available in the case of your practical situation. It is not infinite. And as we said in other case, CMRR. So what is the value of CMRR in ideal? It is infinite, we said. But here, practice, it is not infinite. It should be sufficiently high. It should be sufficiently high in order to meet the basic operational amplifier design. common mode rejection ratio should be high, right? And slew rate, again, the response, the time to change the signal for a given step input or input, it should be very fast. So the slew rate is, once again, it is said to be as high as possible. These are the characteristics of what we can say ideal and practical operational amplifier. These are important. The thing is, what is the difference between ideal operational amplifier and practical operational amplifier? What are the characteristics of ideal operational amplifier? What are the characteristics of practical operational amplifier? So in that case, we need to list out all these things and try to remember which parameter should be high and which parameter should be small. The high, in the case of the parameters such as input impedance, open loop gain, bandwidth, CMRR, and slew rate, these parameters should be high. So which one should be low? So that is Z0, output impedance should be low as possible. Clear? Hope you understand this two types of ideal and practical operational amplifiers. Now we dive to on one more concept called characteristics of operational amplifier. So what are these characteristics which we have stated in the previous case? Are the characteristics for a given ideal amplifier and practical amplifier. If the amplifier is ideal, what are the characteristics? If the amplifier is practical, what are the characteristics that we have seen? And now we are going to see the basic characteristics of operational amplifiers. They are of two types. One is DC characteristics, and another one is going to be the AC characteristics. So what are DC characteristics and what are the DC characteristics that we are going to see? The DC characteristics are nothing but biasing. So how we are going to discuss about the concept of DC? DC is all about the applied or application of biasing voltage. Nothing but we have two types of biasing. One is VCC, another one is minus VEE. In the context of this biasing voltages, we are going to determine the characteristics. So these characteristics are said to be DC characteristics. Are basically of four. What are the four DC characteristics? One is input bias current, preferably base, we will say, input bias current, input offset current, input offset voltage. Also we have output offset voltage, which is called VOS, which we call as VOS, which is output offset voltage as another parameter. And finally it is going to be the thermal drift. These are the four important characteristics that comes under the category of DC characteristics of operational amplifier. What are they? Input bias current, also call it as input base bias current. Second one, it is input offset current, input offset voltage, it is output offset voltage, and thermal drift. These are the four basic characteristics of the DC that we are going to see one by one. Now let us discuss the first parameter, first quantity, which is input bias current. What is meant by input bias current? So it is defined like this. The op-amp input, what is the input to the operational amplifier? It is a differential input, right? So which may be from BJT or FET. The transistors which we are going to use to design the differential amplifier can be BJT or it can be BJT, FET or BJT. And in an ideal op-amp, we assume that there is no current is drawn from the input terminals. The base currents entering into the inverting and non-inverting terminals. So what are the currents drawn in the case of what are the currents that are available in the inverting and non-inverting terminal? So if we consider this as our differential operational amplifier, we have inverting terminal and non-inverting terminal. let us assume the currents available at inverting terminal B, IB minus, and the current available at non-inverting terminal B, IB plus, are the two biasing currents, right? Suppose we are using a BJT transistor in the input stage of the operational amplifier, right? Now, even though both the transistors are identical, so here we are using a differential amplifier. So which means a minimum of we are going to use two transistors. Let us say Q1 and Q2. We have two transistors. So one is responsible for the biasing current, let us say IB minus, and another is for the biasing current IB plus, let us say. And both the transistors are identical, or it can be symmetrical. So which means they are designed from either silicon or germanium material. Their HFEs are also identical. The current gains of both the transistors are identical. However, the amount of base current of these two transistors, Q1 and Q2, are not exactly equal. It is due to the internal imbalance between the two inputs. However carefully we consider two transistors, there will be a slight deviation. There will be a slight deviation in the currents drawn or currents in these two transistors. As we are talking about the biasing currents, IB minus and IB plus, they must be different. However, they are symmetrical. The transistors used in the circuit are symmetrical. It is purely because of the internal imbalance in the circuit design within that differential amplifiers, right? And of course, the manufacturers or designer will specify the amount of IB for a given transistor. And when we use it in the practical situation or when we are conducting any experiment with that transistors, you can experience the difference in the base currents. At least there will be a change or difference in a few milliamperes. Okay. Now let us consider an inverting amplifier. What is by inverting amplifier? If you observe the circuit, the input is connected. What is the input? Let us say this is the input. This is Vin. The input is connected to the inverting terminal. So you can notice the minus. Since we have two input terminals, one is inverting and another one is non-inverting, the input is connected to, if the input is connected to inverting terminal of the op amp and the non-inverting terminal is connected to ground. Suppose if the non-inverting terminal is connected to the ground, then such an amplifier is called as a inverting amplifier, because the input is connected to the inverting terminal of the amplifier. In order to analyze this input-based bias currents as a part of our DC characteristics, let us consider an inverting amplifier. So where inverting terminal is connected to the source, which is Vin, and non-inverting terminal is connected to the ground. And as usual, here we are going to get the output voltage V0, and there will be a feedback. There will be a feedback path between the output terminals and input terminals, which is RF. RF is the feedback resistor, and R1 is nothing but the input resistor. So there will be some amount of current I1, through the resistor R1, right? And the two bias currents are defined as IB minus across the inverting terminal and IB plus across the non-inverting terminal. Now one general question, since non-inverting terminal is connected to the ground, how we are going to define the bias current IB plus across the non-inverting terminal? If I say IB minus across the inverting terminal, it is a meaningful statement. And suppose if somebody say IB plus the bias current which is available across the non-inverting terminal, then what is the explanation for it? So the design of operational amplifier is such that, so there will be some virtual ground scenario. So which means virtual ground as well as virtual source. So if any of the input terminal is connected to some source, there will be some virtual source are truly available in the other end. That is another source also across the non-inverting terminal. Suppose if we apply input to the inverting terminal, there will be some virtual source available for across the non-inverting terminal also. So this is the statement that is there while designing your operational amplifier, in the design concept of the operational amplifier. So this is our basic circuit to consider or to discuss the input bias currents present in the operational amplifier. So with respect to this circuit, we will explore further. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.